What inspires you most at Sega?
What inspires me most at Sega is knowing that everybody at least interacted with Sega technology once today without even noticing.
We are the embedded experts because we have a solution for every embedded problem.
You can see us as a tool provider for other people that also make products. So if you build a house, you need a hammer, you need a drill. We are that kind of company, but for software engineers.
Debug and trace probes, production tools, embedded software and software tools. Our vision is to simplify everyday life for engineers and end users.
People using these products are developers all over the world working with embedded systems. Our market-leading J-Link debug probe is the one piece of hardware that you will find on every embedded developer's desk.
Sega technology is inside everything. Space research, medicine, robotics, motorsports. You can find Sega everywhere.
With our technology, I hope we make people's lives better or easier.
My main motivation is seeing all these projects come to life and change the world or improve the world. Sega is the professional home for so many different people.
Developers, makers, engineers.
What unites us all are three words.
It simply works.
Thank you. Hello, my name is Niklas. This is a very long room. Hello in the back. Yes, they can see me. Okay, great. My name is Niklas. I like microcontrollers a lot, which is a little weird. Microcontrollers Anonymous here. My name is Niklas. Hello. I studied computer science at the RWTH Aachen. I did some autonomous robots in 2010. Out of this Roboter Club Aachen, we created the modem library, which is a C++23 library. Which uses a code generator for 3,700 Cortex-M devices, most of them STM32. It's data-driven, a lot of cool stuff going on there. I then got bored and I started working at ARM in 2015, and then I got bored and started working on railway signaling, model railway signaling, because, of course, there are some really cool, fancy 3D models that you can find there on my website. And then I got bored of that, and I also finished studying because I got too old and it wasn't funny anymore. And so I started working at Auterion. And Auterion is a company that produces an autopilot called the Skynode for commercial drones, big commercial drones. And it combines a Linux system with an STM32H7, and my job in particular is to debug that STM32H7 microcontroller, and it runs NUTX. It's a 2 megabyte binary, so there's a lot of stuff in there. It runs at 480 megahertz, so it runs a lot of stuff in there, and it's very fast. And it's difficult to debug this because, you know, printf is relatively slow compared to the millions of events that we can generate on this 480 megahertz CPU. So I would like to talk a little bit more about the tracing tools, the real-time tracing tools that we develop at Auterion, and that first starts with defining what a microcontroller actually is. So the important thing is that it's not magic. It's a micro CPU, as you can see here on the left, the green thing, which is very fast, and then it has an internal bus, and basically everything is abstracted through a bus system. So you've got a bunch of peripherals, like the external Ethernet MAC, which is connected to a bunch of pins, and then you also have a bunch of internal peripherals, like the random number generator, which is down there. Some hash engines, some encryption engines don't need external pins. But the interesting part is those pins, which are directly connected to the CPU. Those are the debug pins, the SWD and trace pins, and we're going to talk about this. So what do you do with that? Well, there is the SWD, the serial wire debug protocol, which you connect to a hardware debug probe, something like this, in case you work with PX4. Anybody work with PX4 here? Wow, tough crowd. Okay, I brought a bunch of like goodies to give away, but they only really work with PX4, so I guess I'll take them back. This is an ST-Link V3. It costs like 11 euros. It's the most capable debug probe that is very, very cheap. It works fine. You connect this via the SWD pins. Those are 2 pins to the STM32. And then on the other side, you have a USB plug, and this connects to a GDB server. And this GDB server is OpenOCD, or it's PyOCD, or it's a J-Link GDB server, in case you use a J-Link instead of an ST-Link. And then this GDB server actually connects over TCP to GDB. And yes, that is the actual logo of GDB. I don't know why, but that's the logo. And in order to do something with GDB, you can now use the text, the TUI interface of GDB, but it's usually wrapped into an IDE like VS Code using the GDB machine code, machine interface. That's what it's called, which is an ASCII-based interface. And this typically is how you interact with GDB. And this is fairly standardized. Like you have different types of GDB servers. You can do this remotely on non-microcontrollers, normal computers as well. But for tracing, there exists no standard infrastructure. It's basically like you take these trace pins, the SWO pins, which is a serial connection, and then the trace pins, which are a parallel connection, and you connect them to something like a trace hardware thing, which is the ORB Trace Mini in this case, or if you're sponsored by Sega, also a JTrace, which is 10 times more expensive. It's great. Yeah, we're gonna get sponsored by Sega again, aren't we? And then you also connect this to USB, and what is this trace tooling? What is that? It doesn't really, it kind of sort of exists, but it's a very niche part of embedded software engineering. So let's have a look a little bit more about like profiling, about tracing. The absolute simplest way to profile a microcontroller is just to use printf and to log everything out, which sucks. It's slow, it takes a lot of CPU time. Printf can allocate memory if you use the new lib version. So all of this sucks a little bit. It's way too slow for 480 megahertz CPU. Like, it's not even close. So obviously people have thought about this. In the case of NUTX, there is actually a trace subsystem. So the scheduler itself has hooks, and these hooks you can hook, and then you can trace something to a file. Which is still on device, right? So you're still doing all of the tracing and the formatting on device. It's just a little faster. And you can then output this to something like Trace Compass. There's a talk tomorrow at the same time about Trace Compass as well. So I'm not going to go that much into detail. And then, you can debug your code, your RTOS. It is CPU intensive though, because you're still doing everything on device. So can you reduce this? Yes, our friends at Sega developed the real-time transfer, the RTT, which is actually a really neat idea. Basically, it's just you put a ring buffer in SRAM, and you have the SWD debug probe just pull this ring buffer. And this actually works quite fast. They claim up to 2 megabytes per second over an SWD. Which you need anyway to debug the connection. So having 2 megabyte transfer per second is actually a really, really cool idea. Unfortunately, the system view stuff is proprietary, so kind of hard to hack. Probably if you ask Sega nicely, they will let you hack it, but we're not going to do that. So again, we're going to get sponsored by them next year, aren't we? So wouldn't it be nice if, so you still need to do the timestamping, you still need to do the serialization in software, right? So wouldn't it be nice if you had some hardware for you to do this? And that's exactly what the ITM does on the Cortex-M. So there is a dedicated peripheral inside the Cortex-M, inside every Cortex-M except the M0, but who uses that? Exactly. And what it does, it gives you at a very basic level, it gives you 32 channels in which you can write 8-bit, 16-bit, or 32-bit values. And then the entire framing, the timestamping, the serialization is done in hardware. So it is very little code that you actually need to write, and you don't need to deal with serialization and timestamping yourself. You can also see here, these are different types of packets. It's from the ARM. ARM really likes 3-letter acronyms. You have to know this. It's the Architecture Reference Manual, the ARM. So it's all open. It's not open source, but it's open, it's free, and you can see that the overhead per packet is 1 byte. So you're hardly going to get anything more compact than this, and you should definitely use this. You can also get information about exceptions, entries, and exits using the DWT peripheral, which is similar to the ITM. And you can also get program counter samples. So if you want to do a statistical analysis of what your code is doing, you can do that using the DWT. And it's a relatively easy way to do that because it's basically done for you in hardware, and it just falls out this packet, the PC packet here, and then you need to interpret this. There's also instruction tracing. And this is really what you would call tracing. The rest of the stuff is more like profiling because you're not really having a full take of the entire program execution. And tracing here, you're just looking at everything. And this is obviously going to be a lot of bandwidth. If you were to output every instruction that the CPU is executing, then at 480 megahertz times 16-bit per cycle, let's say, because we have 16-bit instructions, that's going to be a shit ton of data. So we're not going to do that. Instead, ARM thought a little bit about this problem and said, okay, actually, the instructions that are in a linear run are all known. You know the firmware on the device from what you programmed into it, so we only really need to instrument the branches. If any of you have done fuzzing, this is how fuzzing works, by the way. Fuzzing also only looks at the branches, right? Something like American Fuzzy Lob. So there is a really cool research paper that basically doesn't even do any tracing. It just looks at the branch information. It doesn't even compute the instructions in between and just does fuzzing on that, which is really cool. You need to, if you want to have the entire instruction trace, you need to actually run a program that looks at the branches and puts them in relation to each other and in the program flow and sort of follows along the program flow. And this is relatively complicated to build. You can see here that the bandwidth requirement is also relatively high. So we're looking at 0.4 bits per cycle on ETMv4, which is the trace protocol for Cortex-M7. There's also a previous version, the ETM 3.5, which is used for Cortex-M3 and M4, which is 1.2 bits per cycle. So this is a significant improvement. Unfortunately, the Cortex-M7, or well, fortunately, the Cortex-M7 is a dual issue CPU, so it can process up to 2 instructions per cycle, which makes instruction timings a bit weird, right? Because some instructions take 0 cycles because they're executed with the previous instruction. There are also some tricks in branch prediction and in the pipeline scheduling so that certain conditional instructions are just ignored, removed. They take 0 cycles. And so the timing here is basically a differential cycle count between the different branches. So you do not get per instruction timings, you get per branch timings, basically. This is at 480 megahertz, which is currently, I think, the fastest Cortex-M7 that they produce, that ST produces. It's 200 megabits per second maximum, right? So it's the literature says something like 0.35 bits on average, and I'm computing here with 0.4 worst case. This is only instruction tracing. You only get instructions out of this. You do not get any data tracing out of this whatsoever because data tracing is simply not implemented. It is an option. Some of the automotive vendors implement this for Cortex-M, but ST does not, which is, in my opinion, a bit of a shame. So you need to go and use the ITM again to instrument all of the data that you want to get out of this. And this adds another 250 megabits. In our case, it's like 40 to 60 megabits. And you can see that this combined bandwidth actually fits well into USB 2. And this thing is only USB 2 because it's easier to produce than USB 3, like significantly easier. And the JTrace is USB 3, so if you want to use the full bandwidth of this parallel trace port, you need to use a JTrace. But even for an H7, which is the fastest that they produce, USB 2 is enough. So let's have a look at where this data actually goes, because 250 megabits per second is a lot of data. This is the debug and trace system of the STM32H7. It's fairly involved. You can connect your debugger. You can see the DWT and the ITM and the ETM peripherals connected to the CPU here. You can also see that they have the internal buses in black bars, and then in gray bars you have the data outputs. You can see them going out on the right. So a normal debugger would connect to this side, the left side, over SWD, and then you can use, you can access the internals of the CPU and the internals of all of the memories using the debug access port buses. This is pretty much how every debug port works on Cortex-M, right? It's just you have access to the buses, and then that's how you work with this. If you want to get the ITM data out, you can use the onboard 4 kilobyte FIFO, the ETF. It's a lot of RAM, 4 kilobytes just lying there. Unfortunately, you cannot really use it from software. You have to only use it from the ITM. And then you can read this out over the debugger. And this is basically a hardware accelerated RTT, if you think about it, right? It's also a ring buffer, but it's all done in hardware. This is still relatively slow. Like even if you use a hardware accelerated debugger, it's probably only going to be a few megabytes per second. So instead, you can also reroute the ITM output to the SWO pin, which is a single pin. It's a single pin that outputs UART. So you can already use a slow UART to capture this, so you can use it as like a printf, a hardware accelerated printf, which is a bit of a waste, but you can do that. Or you can output up to 60 megabits. With this thing, you can capture a 60 megabit output, so a 6 megabyte output, because UART is 10 bits, right? Or if you want to use the fast port, the parallel port, using the ORB trace, you have to go through the trace pins. And this is up to 4-bit parallel port. It's 1-bit, 2-bit, or 4-bit, up to 1 gigabit per second in bandwidth. This thing can capture it. Of course, limited to 400 megabits of USB 2, which is not a problem, as we saw. So how does this look in practice? Well, this is what I'm currently using. I didn't have the time to develop a PCB, and so I just took a soldering iron. None of this is length matched, by the way. It still works fine. Yes. Yeah, I know. Yeah, I should probably use some electrical isolation there as well, but it's fine. This thing only costs like a lot of money. Yeah, so on the left, you can see the STM32H7. That's the actual autopilot. The thing on the right underneath, the ORB trace, that's the Linux computer. Apparently, that's what makes us money. In the middle, you can see my very, very length-matched connection here. So even under not the best condition, this actually still works pretty fine. So I don't get any bit errors even at tracing at 1 gigabit per second. So lower your expectations of like length matching. As a software engineer, I know hardware, okay? Don't listen to me. What does this look like specifically more? Like what you get this data stream out of there. It has framing. You can separate out the ITM from the ETM. And then you have 2 separate streams. They're synchronized using the same timer, so you can synchronize them. The ITM is something that you define in software, so you have to figure out what data you want to get out of the Cortex-M, out of your software. You need to instrument it accordingly. Choose wisely, I can say. and choose compactly because you don't have infinite bandwidth. In particular, you also want to choose channels that you can output only over SWO, over the single pin interface, because having the parallel trace port requires 5 pins, right? It's a clock and 4 data pins, and 5 pins is sometimes quite a luxury to break out on a board. So at least break out the SWO pin, at least use the ITM. And then, of course, you've got the ETM stuff, which is a lot. It's complicated. There's like a 1,000-page PDF, of course, because it's ARM. And so it's very detailed. It goes into all of the details of this protocol. And then, of course, you have your ELF file because you need to know what instructions lie between the branch information and the debug symbols and all that stuff. This is currently what it looks like. There's the people who designed this hardware also designed a software library called Orbiculum, and we created the portemonnaie of Orbiculum and Perfetto and called it Orbetto, which is not an ice cream. It's the #1 thing that people tell me. Call it Sorbetto. No. We need to use the disassembler. We use the Capstone engine, which is a standard thing. And then we transcribe this into ftrace packets, which in the dialect of Perfetto, because then we can use all of the standard tooling from ftrace, and this is exactly the point, right? We don't want to reinvent all of our own trace tools. We just want to get it into a format that's sort of semi-standardized and then use whatever the Linux people are using. You can see that it's a lot of data. Like if we want to trace the raw data, it's over 100 gigabytes per hour. For us, it's not that much of a problem because our batteries are so limited that we're not going to fly for an hour. Thank you, battery technologies. But if we don't trace every instruction, instead we only generate call stacks. So every function, which is relatively long, so the number of instructions in a function is much larger than the string of the function. So we can reduce the bandwidth to like 50 gigabytes per hour. This is only interesting if you run it in CI, right? Like obviously if you fly around, you're going to capture all of this once, but if you actually have like 10 racks of your CI running this, then you need a few terabytes of this stuff. So what does this look like specifically? Like this. This is Perfetto. You can go online and try this out yourself. There are it's a web-only tool. It uses WebAssembly, and you can just drag the file into the thing. You can see at the top there is the CPU usage of the entire. We only have one process because it's an STM32. It doesn't have multiple processes, so we only have one CPU. And you can see the scheduler doing its work, including all of the interrupts. This file was captured using the SWO pin, and you can see one thing. There's an SVC call interrupt there at the top middle third, and it's very long, and this is a false positive. The problem is that the ITM prioritizes certain packets, and the interrupt exception entry and exit package are very low on the list, so sometimes you just don't get the packet that an interrupt exited. This is something you need to keep in mind. It's not a problem for the parallel trace port because it's got enough bandwidth. But yeah, on the left you can see all of the threads. PX4 has a lot of threads, so this is only a subset of them. And then you can see something like this thread, which also has a work queue in this case. It doesn't have rendered call stacks here yet. And it's very fun to look at this, scroll around, and just see how an RTOS works, because you can see every scheduling, every interrupt, every event that goes on. And just by looking at this with your eyes, you can already see patterns, and it's very easy to see something that's disturbed. Of course, you can trace anything, really. I mean, for example, you want to trace every malloc and free call? Yeah, sure, be my guest. Here's every point here is a single event of malloc and free. You can see this down here. There is the address that was allocated and the size and when, and then we can add and subtract this together and we get the total heap usage. Other tools do this too, right? It's not rocket science. We can also trace other stuff like DMA channels and semaphores. Here you can see the SPI3 workqueue at the top. You can see that it was triggered by a timer IRQ, and it was scheduled out by the SVC call again. So it itself scheduled itself out. You can see that it starts 2 DMA transfers, one for the MOSI, for the output going, and one for the input going. And then it just goes away. It waits on a semaphore, on this semaphore, and the DMA transfer at the very end posts the semaphore again, if you look further on the right. As I said, it's very easy to see patterns with your eyes. So in this case, you can see a brownout event when we put too many sensors on a particular power rail, and during certain operations, when they all do the same thing, the same measurement, they brown out. And it's something that only happens in the field, and it's hard to test on the bench because our power supplies are better on the bench than the batteries. And so this is something that you would catch. And it's very easy. You don't even need to like think. It's just, oh, this doesn't look right. And then that's it. But it would be nicer if instead of saying this doesn't look right, is there something more scientific or, you know, anything better than just your eyes? Because my eyes get tired a lot. And so Perfetto has this concept of querying traces. And they chose the SQL language, specifically a dialect of SQLite. And they wrote their own query engine in C++, and it's extremely fast. And in particular, it gives you an interface for dealing with traces, which is a problem that a lot of other tools just don't give you. Like, they give you an instruction stream. Maybe, if you're lucky, they give you a timeline of events. And then what? What am I supposed to do with this, right? Perfetto actually gives you an SQL, and even though I personally don't like SQL that much, at least it's standardized, right? We're not reinventing the wheel. There is a fantastic talk about this entire concept and how Google uses this, Perfetto is written by Google, to debug the Android operating system. And I strongly recommend that you listen to this talk. It's only 30 minutes long. One thing to note is that this is really only useful for integration tests. So you can test all of your threads and modules in isolation, but then when you put them all together in a complex system like we have, you see certain behavior that you wouldn't otherwise see, and that is hard to test in an integration test. And we have a 2 megabyte binary that we would preferably not modify, right? We do not want to have a test version of this binary and then a release version, because the release version is not tested really. I mean, you assume that it's the same binary, but it's not. And so the instruction tracing gives us a way and the ITM gives us a way to, from the outside, interrogate the behavior. And so some of these queries give you a lot of data, and in general, you know, this is 45 gigabytes an hour. So there's just a lot of stuff in there, and it would be nice if you can reduce the complexity of this. And so the thing that we really want is something that takes a bunch of code changes, like a pull request, and you know how pull requests are, right? You get an idea, you push it on GitHub, and then you think about the problem, and then you realize, oh, this is completely wrong, and then you push immediately a second update, and then you realize, no, that's still not right, and then a second and third. It's just me? Oh, okay. So that's basically sort of the list of things, and you want to filter this out. You only want to look at these traces in isolation. And then you want to map your queries onto this. So the queries that we're interested in, for example, are the sensor readings regular, because we have a 400 Hertz control loop, and it's relatively sensitive to variations in the sensor readings. It's typically not a problem, but if you change like thread priorities in different areas, sometimes you can have adverse effects. We want to have a certain minimum guaranteed throughput for DMA. And depending on where you call this from and what priorities the DMA channels themselves have, because they also arbitrate, you can have changes in throughput, even though you changed code completely different area. That is something that, as you've seen with the DMA channels, we can also look at. We want to look at the scheduling latency sometimes some low priority tasks don't get scheduled fast enough because they're low priority, right? The RTOS is doing what it's supposed to do. But these low priority threads also have timeouts for these waits. And sometimes in some unfortunate circumstances, these timeouts get triggered. And it would be nice to have an understanding of like how often this happens, what the distribution of these timeouts is, so you can choose a value that actually makes sense. It's not just a guess, it's something that you can measure. Obviously, the classical thread progress, you don't want to have deadlocks with semaphores. That's always a classic. Somebody adds a semaphore somewhere and whoops, the whole thing blocks. And something that was also interesting is we sometimes have functions that need to be called in pairs, enable and disable. Typically in C++, you would do this with RI. In our case, we have to deal with a C scheduler. NATEX is written in C, so that doesn't always work. Cannot wrap everything in C++. And so it would be nice to also retroactively look at traces and check if the functions were actually called in pairs or if there's some imbalance. And then you take this and throw it into a graph. And you can see this is a standard filter map reduce pipeline. And at the end, you either want the graph to be higher or lower than before. Very standard thing. It's also something that Perfetto helps you with because they give you a batch processor that does the map reduce pipeline specifically for this. And why don't we just do this on device, right? And the answer is because you need to know what metrics you need to capture before you actually capture them, right? Because they're on device. With the instruction trace, you capture all of the instructions. You get all of the call stacks. And so you can go back in history. I know this is like time travel, but stupid. You can go back in history and look at the stuff. And you can run new queries on the old traces that we have in our CI. And with the power of hindsight, I can tell you this is a great idea. So that joke fell flat. So what is the future of this? Because at the moment, we obviously have more stuff. We also do on-device logging, but it's only the stuff that we thought was important or that in the past we had issues collecting data, so we added it now. And we collect this. We do in-flight monitoring. We do post-flight log evaluation. I do a bunch of bench testing, and of course we do the CI tracing, and you can see that all of them have like different data formats. The in-flight monitoring is written in C++, so I guess binary. We have a format called ulog, and the analysis tools for all of these things are also different, right? We have something called the plot juggler, which reads this ulog and then accesses the plots. The post-flight logs are very coarse, of course, right? We don't have megabytes of bandwidth. It's an STM32, so we have like a few hundred kilobytes of continuous logging. So it doesn't contain that much data. But it would be nice, because we only in this talk looked at the lower part, right? The PerfettoSQL. But all of the other logs and data that we have is also important, and it would be nice to not have to like write all of the SQL code and then have to rewrite the same queries basically in Python and then in plot juggler and then in C++, because that would be stupid, and software engineers are lazy. So maybe there is a better solution, and I started looking at research, and there appears to be something called RT-LOLA, real-time LOLA, which you specify the query once, and then you compile your queries to different analysis tools. So to put it in a meme form, one specification to rule them all, and in darkness bind them. These are some pretty figures that I found in these papers. This is what I would look at next. So you can see here, you've got your specification. This is the typical, computer science stuff. Let's make it formal, and you have a formal verification, and then let's just compile it. And then the compilation is usually the hard part, right? The specification is easy. But the idea here is that you have an interpreter which you can run on the logs, so it's off-device, post-flight. But you can also compile this into a monitor that runs on-device, perhaps even on the Linux computer. So you can do like instruction tracing from the STM to the Linux computer and then run it on there, assuming that the Linux people allow me to do this. So that's basically where we're at. Some of these things are not fully implemented yet. It's complicated. You basically have to be an expert at embedded software. You have to understand how data science works. And you also have to be a bit of a quality engineer to understand what actually is important. And so this is very much a niche within a niche, so difficult. The Cortex-M debug and trace hardware is very cool. It's very cool. I mean, it is shipped with every Cortex-M device. Please use it. It's so cool. I also want better tools, right? So please help me write better tools. Perfetto is great. It's getting better. It's getting much better. In the last year alone, I have fixed so many bugs and added so much more cool stuff. You can use the UI offline. It has a C++, a fast server implementation of this as well. So you're not limited to the WebAssembly memory. I think it's like 2 GB memory limit on Chrome. And this entire concept is a fantastic promise. Just this is very clearly the right idea. I'm sorry, I don't want to toot my own horn, but it's very clearly the right idea, right? You want to go into a standardized direction. You do not want to reinvent all of this stuff yourself. Go to ftrace, go use Perfetto. It's great. And this thing works really well. The software is not that great, but the hardware works really, really stable. I'm working on improving the software. All of this stuff is developed open source, so if you want to go to the embedded debug tools, you can do so. Keep in mind that there's also this is the second part of these tools. The first part of these tools are writing Python GDB plugins, which I've given 3 talks already, so they're all on YouTube. You can look at this. And this is also pretty cool. Extending GDB itself is also extremely helpful, and you should all do it. And that's it. Do you have questions, and can I throw debuggers at you? Unfortunately, they only connect to PX4.
So that looks powerful. Thanks for that. I was just wondering because another tool which I'm used to using a lot for the profiling is Linux Perf. I was just wondering whether you have integration with it, or
no.
There's a Perfetto data to perf data tool or something like that.
So I'm a bit sad that the Perfetto tool doesn't just use ftrace. I think there is a converter for converting ftrace directly to Perfetto, but I would have liked to just generate an ftrace and then have all the tools work with it. It's probably not too much work. At the moment, it uses like a protobuf implementation to convert the ITM traces to Perfetto ftrace format. So the code is open source. It can be changed. At the moment, I have such limited bandwidth because this is not really my job, right? My job is to not develop research, but like to actually do things that are profitable. So yeah, I have limited bandwidth. So I only made it for Perfetto. But yes, it would be very nice to use all of these other tools as well.
Cool.
Run, Stefan.
Okay.
You spoke of having your production firmware and then testing firmware be the same so that you always have the tracing. How much of an impact does the tracing have on your runtime performance? And are there other associated risks with keeping that information available on those pins, like from a security perspective? Or
security-wise, we don't even lock down our devices. Like if you get physical access to the drone, then you can do whatever you want with it. But that's like you don't have to hack into the drone to use it. Like the entire ecosystem of like wireless communication is not so secure, and it's a bit like hobbyist hardware sort of meets the professional market. So like we'll deal with the problem of security when it actually becomes useful from like a multi-layered approach. You need the ELF file to make sense of the trace output. You can probably gather some information, or you can probably gather information without the ELF file, but it really only makes sense with the ELF file. So unless if you get some device that outputs trace information, yeah, it might be useful, but probably not that much. In terms of, what was the first part of your question?
The performance impact.
The performance impact. So the first thing is you can turn it off. So the instruction tracing in particular is a hardware feature, only a hardware feature, so it has no impact on performance. The ITM depends a little on how much bandwidth you have available. So you have to wait. It only makes sense to output all of the ITM stuff if you wait for it, right? So if you miss a few scheduling stuff, then it gets out of sync. So you have to wait until there's space in the buffer. And what I didn't tell you is that the SWO pin, the SWO serializer only has a 10-byte buffer. I don't know what ARM was smoking, but 10 bytes is not enough. It is a dumb idea because you always wait until there is something free in the buffer. Which is why using the ETF, the 4 kilobyte buffer, makes sense if you have a slow connection out. If you use the trace pins, there is no impact that I can see, because there's always space. Like you have so much bandwidth, a gigabit. I don't even know if you can actually produce that much internal memory. You can? Oh, okay. You can apparently. Yeah. Okay. But yeah, a normal usage in parallel tracing, it's no impact. In SWO tracing, I saw maybe a microsecond or so delay in some of the scheduling switches, because it has to wait until 5 bytes or 3 bytes, depending on what size you put in there, are free in the buffer. I don't know, again, what they were smoking. It's such a dumb idea. But yeah, it's only one pin, and it's probably very cheap to implement in silicon.
So Nino is now going to explain how much that talk costed us.
Oh boy.
So first of all, thank you for the talk, very detailed. I liked it a lot. First question, you said you were also doing the trace while the drones were flying. Did I understand it correctly? If yes, very good soldier job.
I haven't convinced the hardware people to let me touch the drones yet. I don't know if this picture had anything to do with it.
Okay, gotcha. And then about Perfetto, if I understand correctly, this will it strips all in between. It just shows you the high-level events, right?
Yes,
so you
it doesn't show you instructions.
Okay, I gotcha. So just to get an overview and see the patterns, essentially, what you were talking about.
Yeah, so we had this discussion internally as well, like how useful are call stacks when you have internal branches of functions? Because I told you, like, you cannot get the data out, but you kind of can get the data out. You can at least get Boolean data out whenever a branch was taken, and depending on what the condition was of the branch, you kind of have restrictions on the data. There is some cool research on this, which leverage symbolic execution, something with the CLE engine, I remember, that tries to reconsolidate all of these different constraints in order to give you a more clear picture of what the data inputs were. Most of this is done in the context of fuzzing, because that really makes sense there. But for our stuff, like, let's start with simple function names. Like, I'm already trying, it's already breaking my brain to think about all of this stuff. But the thing was, so I actually have a JTrace. You're from Sega, right?
Yes.
Okay. So I tried to use Ozone, which gives you all of this stuff, but I didn't find the instruction trace to be that useful, because I can already get the instructions from the disassembly. Mm-hmm. So of course, it's useful to see which branches are taken, but once you hit like a while loop, bam.
It gets big, right?
Yeah. It's so... I'm not entirely convinced that looking at the instruction stream is necessarily that good if you do not have a higher level abstraction. Right. So we started with call stacks.
No, that totally makes sense. You would only want to, let's say, if you need the complete backtrace, you're probably in trouble because you run out of options.
Yeah.
Okay, so
yeah.
But if you can catch it in analysis earlier, you want the high level view. Yes.
Yeah. So the ETMv4 decoder in ORB code is buggy, and I think it was written by volunteers, so I can't complain really. It's free, but we're fixing this at the moment. So specifically, my intern is fixing this. He's doing all the work, as always. Yeah.
Okay, thank you.
Any other questions? Doesn't look. Oh, yeah. Paul has another question.
So just quickly about the branches. As far as I remember, ARM assembly, you have like if then else blocks and stuff like that.
Yes.
Is that covered as well?
Yes, conditional execution. Yes, conditional execution is something that's not really a branch. It's like a pipeline flush, I guess. Yes, that also has a specific. Here you can see the conditionals. That's the one. You also get addresses sometimes if the jump is too large, or if there are like specific like exceptions, for example, interrupts or something where it doesn't have any, it just happens. And so you get more data out of that. Again, the branches is very simplified. I mean, the details are long. It's particularly fun if it has a data trace on there, because then you need to like synchronize the data access reads and writes with the instruction trace. And if you know Cortex M7, it has caches, so the data accesses happen sometime later, and then you need to like reconnect them back. Ooh, yeah. All right. More questions?